starting with the nebula, what did I say the nebula is? Dust particles. Now, the dust particles are pulled together by a force of gravity. You know, the gravitational force crushing them towards the center. As that happens, there's so much pressure and heat at the center, the core. Right? That much heat at the core will cause what we call nuclear fusion to begin to occur. Nuclear fusion. Yes, we've done something about nuclear radiation. I told you about nuclear fusion and nuclear fission. Do you remember what nuclear fusion is? What's fusion? What's fusion? Fuse. Yeah, when smaller nuclei join together to form heavy, excuse me, to form heavier nuclei, and at the same time releasing energy. Right? That's the process that takes place in stars. That's how stars release their energy, through nuclear fusion. But the one we use in a large scale on Earth currently is nuclear fission. So there's a difference between fusion. Fusion is when smaller nuclei join together. Fusion is about joining. I will just use a keyword that you can remember. But the one we use on Earth is fission. Fission is about what? Yes, fission is about what? Splitting. When heavier nuclei split into smaller nuclei, also releasing energy. That's fission. When smaller nuclei join to form heavier nuclei, also releasing energy. That is fusion. Which one takes place in stars? Fusion. Which one do we use on Earth? Fission. All right. Okay, so fusion requires a very high temperature and high pressure. That's why it's still difficult to replicate it on Earth. To produce materials that can withstand the high temperature and pressure needed for fusion to occur is still a big challenge. So it is just at the experimental level in particle accelerators, because the pressure and heat that will be required to make fusion possible is so high that materials that can withstand such heat is yet to be produced, or are yet to be produced. So fusion is not common. It's not currently practicalized. I hope you can hear me. All right, so the fission is easy to replicate on Earth. Okay, so it's fusion that occurs at the center of the nebula because of the crushing of the particles as a result of the gravitational force acting on them. So they crush on each other, and because the force is towards the center, crushing them. When crushed so much, the pressure and heat generated at the center will make fusion, nuclear fusion, to begin to take place. And what it simply means is smaller nuclei like hydrogen will join and form heavier one like helium and releasing energy. I need you to read this main sequence, what we call the main sequence star. You may need to scroll to the right, left a bit to reveal it. Yes. You know, I talked about, hold on just a moment. I talked about the inward force of gravity. What direction does the gravitational force act? What direction does the gravitational force act on the nebula? Inward. Now, once that force has generated sufficient pressure and heat, fusion will begin to occur. And fusion also releases energy. Releases what? That energy released during fusion will begin to produce a force too that will push outwards. And I'm going to represent it with this one. You may need to scroll a bit to the right, to see left, to see what I'm representing. These ones I drew in red are forces produced as a result of the fusion taking place at the center, the core of the nebula. Heat is generated, energy is released. So there's also a force. So while the yellow one, gravity, is pushing inwards rather, the red one, produced as a result of fusion, is pushing outwards. Does it make sense? So I said the red one is produced by fusion. Outward force produced by fusion. Outward force, where can I write it? I think it's better to write it here where I have enough space. Outward force produced by friction. You say you still haven't done it in class. But it's in your syllabus. You can see it's a question you need to answer. So outward force produced, pardon? Oh, not yet. But your exam is just about a month. So we had better finish this. So what did I write as the description of the red arrow? So of course the gravitational force produces inward force. Produces an inward force. So when these two forces balance, the star is stable. That's what we call main sequence star. So you can now read it. When the two forces balance, there's an equilibrium, which becomes, and the star is at that point called main sequence star. Remember, we are talking about this sequence or formation of stars. The sequence, it follows the sequence. The starting sequence is what? The starting point. Nebula. Okay. All right. The gravitational force is the one that acts first. And when it's crossed, heat and pressure causes fusion to start taking place. Fusion is basically joining of two smaller nuclei. An example is two hydrogen atoms. You know, it has a very small mass. And when they fuse together, they form helium. So that fusion will also produce a force acting outwards. And when the two forces balance, if a main sequence star is formed. Okay, so you can now go ahead and read everything about the main sequence star. More quickly. So for the main sequence star, you can see the outward force of gravity and the the inward force of gravity and the outward force of the due to fusion are in equilibrium, so the star is stable, and hydrogen nuclei are fused into helium, and so on. Now, depending on the size of the star, if it is a star less than 3 of the size of our own star, it forms a red giant. Okay? It forms a red giant when the hydrogen runs out. You know, it's hydrogen that is the fuel for fusion. Now, I told you the two hydrogen atoms fuse, forming helium. So gradually, hydrogen is used up in the core of the nebula. So when the hydrogen is completely used up, like runs out, hydrogen runs out, the fusion switches to another element, helium. You know, it was the hydrogen that joined to form the helium. Now, helium now begins to fuse, join, to form heavier elements like carbon, oxygen, and beryllium. And so the outer layer of the star also expands and cools. Okay, then it takes us to the next one, this number 4, what's it called? White dwarf. If the star is still much smaller than the one that forms red giant, but still larger than the size of our own star, the sun. So if it's about less than 1.4 of solar mass, when we say solar mass, we're talking about the mass of our own star. What's our own star for our solar system? The sun, okay. So when a red giant has used up all its fuel, fission stops and the core contracts as gravity is now greater than the outward force. You know, that's what I was trying to explain, but I had to pause until I get there. I told you fission is taking place at the core, pushing outwards. So when the fuel is completely used up and no fusion is occurring, it means the gravitational force is the only one acting now, isn't it? So it will be bigger than the outward force, meaning that it will be pushing it inwards more than the outward force. So it forms a dwarf star, what we call white dwarf. Which force is bigger now? Gravitational force or fusion, the force due from fusion? Inward gravitational force or outward force of fusion? Okay, inward gravitational force is higher than the outward force produced by fusion. So what do you think will be happening? Will it be a crushing or an expansion? Okay, that's why it forms a white dwarf. So when a red giant is used up, all its fuel, fusion stops and the core contracts as gravity is now greater than the outward force. The core becomes very dense. Now a white dwarf will eventually cool to form a black dwarf. And then there's another stage, what we call red giant star. This one comes from a red giant. So when a high mass star runs out of hydrogen nuclei, the same process for a red giant occurs, but on a larger scale. So a red supergiant is formed. Okay, now supernova. This supernova usually occurs when the star is greater than 1.4 of the mass of the sun. And then, of course, all the fuel has run out and fusion has stopped and the core is collapsing inwards very quickly and suddenly, making the core to become very rigid, so dense, because there's an extent you will push something. You are pushing particles together, pushing them together. You get what I'm saying? You are pushing them together. There's an extent you will push them and they cannot force themselves together again because they have reached the point where they can move closer to each other than what you already have. So that core is now so rigid. And because of what happened, the speed at which the thing is pushed together. I need you to read this. Read the second bullet point. It's just like if the roof of a house collapses, collapses suddenly. You can imagine if the roof of the house collapses suddenly. When it lands on the floor, it will rebound a bit. It will rebound a bit, isn't it? It just falls suddenly on the floor and rebounds. So it's that rebouncing that throws some waves into the space. And that is what we know as supernova. That's actually very loud. But luckily, we can't hear anything. We can see the signs of supernova with bright flashes of light. But you can't hear anything here on Earth. Do you know why we cannot hear supernova as loud as it might be in space? Because of what? No, not necessarily. It's about loudness. What you have in space is a vacuum, nothing, isn't it? Can sound travel through space? Sound cannot travel through a vacuum, isn't it? Even if you are close to a star that supernova is occurring, you can't hear the sound. You may not be alive to even watch what is happening, because the stuff that is thrown into space might get you trapped. But you won't hear it, because sound does not travel through a vacuum. But you can see the flashes of light. Why? Because light travels through a vacuum. Did you get my explanation? So the outer layer of the star falls inwards and rebounds off the core, launching them into the outer space in a short wave. As a short wave passes through surrounding material, elements heavier than iron are fused and flung into space. The remaining core depends on the mass of the star. That's how a supernova forms. Now, from a supernova, for a star between 1.4 and 3, the mass of our sun, when the core of a large star collapses, gravity is so strong that it forces protons and electrons to form neutrons. The protons and electrons are converted to neutrons, forming what we now call neutron star. So a neutron star consists of just neutrons. That's why the name is called neutron star. And finally, if it is bigger than 3 times the solar mass, it forms a black hole. You've heard so much about black holes. Have you heard anything about black holes? It's another wonder in the world of science. Nothing can escape the black hole. Even light cannot escape a black hole. If a light is flashing across a black hole, the pull of the black hole is so high that it also traps light. It just disappears. No trace of it, even light. That's why it is called a black hole, because it can't even allow light to stay. It sucks in light, sucks in matter, sucks in anything. The gravitational pull is so strong that anything there is sucked very suddenly into the center. So that's how a black hole forms. So when the core of a giant star collapses, the neutrons are unstable to withstand gravity, forcing them together. The gravitational pull of a black hole is so strong that not even light can escape. Okay, so that's a sequence of the formation of a star. I think we can now attempt that question. What page is it on? Okay. All right. Were you already answering the question? It says, state, what was the first part of this question? Okay, the one we answered earlier. The first part of the question was about something. Let me just remember what it was about. Okay, it started from number 4. It said the sun has a mass of this, a white dwarf has a mass of this. Calculate the value of, all right. Okay. And then we did all this. Okay, so the next part of the question says, state how the brightness of a main sequence star changes with its temperature. Okay, you already answered that. Can you go to the next page? It says, state how the brightness of a main sequence star changes with its temperature. Of course, you know, the higher the temperature, the greater the brightness, based on the graph we worked on in the previous page. That was in our previous class. Okay, so now, state how the brightness of a main sequence star changes with its mass. You didn't answer this one. I thought we also talked about it. Did we run out of time? Of course, without wasting our time, the bigger the mass, the brighter the star. That's the truth. Because the graph shows that stars of higher masses are brighter. So can you just write it down? Do you have your pen tablet? Yeah. Interesting. Imagine, I didn't know that this question was actually waiting for us here. Can you read it out? All right, so nuclear fusion provides energy source for stars, including the sun. Describe what happens during nuclear fusion. Go ahead. Can you say it first of all? Let me correct you before you write it down. Yes. To form, yes, hydrogen atoms were basically nuclei joined together to form helium. From helium, and at the same time releasing heat, tremendous amount of energy. You can write it down, that's correct here. To form what? Fuse together to form, let me add it. Hydrogen nuclei fuse together to form. Just go ahead, let me add that. To form helium. Good. So, excuse me, D. Interesting. A nebula may evolve into a main sequence star such as the sun. Explain how a nebula may evolve into a main sequence star. Well, you can try, you can attempt that question. Just say something from what I discussed with you. Yes, it has to do with nuclear fusion and something. First of all, the first force that acts on the nebula. Yes, the gravitational force acts on the dust particles, pulling them in what direction? In words, interesting. Gravitational force acts on the gas particles, on the particles, not necessarily gas particles, the dust particles, pulling them inwards. So, okay, let me be writing it down as you're saying it. So why does nuclear fission begin to occur? Gravitational force acts on the dust particles. Yes. Sorry. Let me make a slight adjustment so I can write neater. Gravitational force acts on the dust particles. Acts on the dust particles, crushing them inwards. Towards the center. Or the core of the nebula. You know what I mean by core? Middle of the nebula, yes. The high pressure and temperature, results in fusion, which releases fusion, which produces an outward force. Excellent. That's what I'm going to, that's the next point. So gravitational force acts on the dust particles, crushing them towards the core of the nebula. The high pressure and temperature results in fusion, which produces an outward force. Now, when these two forces are balanced, the two forces balance, producing a stable star. You see that? Producing a stable star. Can you just read it out? Yeah, gravitational force. Go ahead. So that's the main sequence. All right, you have your 3 marks. Okay, any other question here? Is there any question we're missing? Pardon? Let me see. It looks like this is the last part of that question number 4 you copied. If it is the last part, then I think we have exhausted. We finished the question. Because this one is a different question about radio waves. Okay, that's fine.